My name is Alexander Braun from University of Bonn in Germany, and I'm very happy to present joint work with Thomas Kesselheim on truthful mechanisms for two-sided markets via profit inequalities. And before we go into the talk, let me maybe first explain what a two-sided market is. Namely, there are sellers with items and buyers, and we somehow want to reallocate the items among the agents in order to maximize some objective. And in the simplest example, we can consider the case of bilateral trade. That is, there is just one seller equipped with one item and one buyer, and somehow the same question occurs. How do we reallocate the item in order to maximize some objective? And we are assuming a setting in which each of the agents has a privately known value for holding the item. So in this example, the seller has a value of 5, the buyer has a value of 8. And as said, this value is a private information, but we assume that they are drawn from a publicly known distribution, which is also known to the mechanism designer. And now we want to design mechanisms with the goal of maximizing social welfare. And in this case, social welfare is just the value of the agent who is holding the item after running the mechanism. And of course, we want this mechanism to satisfy some constraints. And the first constraint is dominant strategy incentive compatibility, meaning that for any agent, it's a dominant strategy to report her true value no matter what other agents report. We want it also to be individually rational, meaning that participating in the mechanism is not harmful, and we want it to be budget balanced. And for this bilateral trade setting, there is a very simple mechanism template. Just fix a price P beforehand, and then we trade the item if both agents agree a trade. So in particular, if the value of the seller is less than the price and the value of the buyer is at least the price. So how does this look like in our example? So again, we're considering the case that the seller has a value of 5, the buyer has a value of 8. And now there could be a mechanism just fixing a price of 9. And then we first ask the seller, do you want to trade the item or not? And the seller, of course, says, okay, I just have a value of 5. You give me 9 units of money in exchange. Hence, of course, it's beneficial for me. So the seller will accept the trade. But on the other hand, the buyer just has a value of 8. And of course, the buyer will say, I have a value of 8, but I have to pay 9. So that's not beneficial for me. Hence, the buyer will reject the trade. So the seller agrees the trade, buyer disagrees, so no trade occurs. As a consequence, the item remains at the seller, and hence we have a resulting social welfare of 5, which is in this case just the value of the seller. Now there could be another mechanism. Just say we have a mechanism which is fixing a price of 6. And then again, the same procedure is starting. So we first ask the seller, do you want to sell the item or do you want to keep it? And still for the seller with a value of 5, it's beneficial to sell the item, so the seller agrees the trade. And in this case, also the buyer will say, okay, I have a value of 8, but I just need to pay 6. So therefore, it's also beneficial for the buyer to accept the trade. Hence, both agents agree, so a trade occurs. And the item is transferred from seller to buyer. In exchange, money is transferred from buyer to seller. And hence, we're resulting in a social welfare of 8 in this case, which is just the welfare or the value of the buyer for holding the item. And what you can see in this example is exactly that as the ex post optimum, you just can trade the item if the value of the buyer is at least the value of the seller. And then you give it to the one who has the high value. But as a mechanism designer in this template that we were considering, when we fix a price P, we somehow, there can be some mistakes happening. So first of all, if the price is too low, then of course the seller will disagree and not sell the item. And if the price is too high, and that is what you have seen in the first example that I was just showing you, then the buyer will disagree and not trade the item. And hence, as a mechanism designer, we somehow have to find the sweet spot in order to balance this price so that it's not too low, but also not too high. And if we want to maximize social welfare, there's even a negative result from the 1980s dating back to Myers and Satterthwaite, saying that there is no mechanism that is incentive compatible, individually rational, budget balanced, and can achieve the optimal social welfare. And hence, as a consequence, what we try to do is we try to find good approximation guarantees subject to being dominant strategy incentive compatible, individually rational, and budget balanced. And of course, we do not only want to do this in the single seller, single item, single buyer setting, but we rather want to consider the cases of multiple sellers with multiple items and multiple buyers. And even further, we would like to see, okay, what can we do if there are additional feasibility constraints over the set of buyers that get items? So for example, if the buyers who get an item need to be independent in a match rate, or if there's a knapsack constraint over the set of buyers who get an item and the set of buyers who get an item need to fulfill this knapsack condition. Or if there are combinatorial valuation functions over item bundles, meaning that any agent might be interested in multiple items instead of only in a single item. Our results in the paper are we design posting pricing mechanisms which are all dominant strategy incentive compatible and individually rational, and which improve approximation guarantees in many settings. So we have seen this bilateral trade case in the introduction and the talk, and that's just a special case of all of our results. And hence we get like a 1/2 approximation for this case, which is still not the best because you can even get a 1 minus 1 over E approximation, and you can even improve on this by a small constant. But for measured double auctions, combinatorial double auctions, and knapsack double auctions, we are able to improve the state-of-the-art approximation guarantees in all settings. And in particular, our mechanisms ensure either weak or strong budget balance condition, meaning that in the weak sense, we cannot subsidize a trade as a mechanism designer, but only can extract money from trades. And in the strong sense, it means that all the money that is spent by buyers needs to be transferred to sellers. And as an additional feature, the majority of our mechanisms can be implemented online, meaning that the buyers just arrive to the market, we offer any buyer a trade, and then the buyer is leaving, and we do not consider this buyer for a second time. The only mechanism that is not working in an online way is the first mechanism for measured double auctions, which is strongly budget balanced and a 1/3 approximation. And I will tell you a little bit about this mechanism later in the talk. But first, I will discuss quickly how our approach compares to previous approaches. So therefore, let's go back to the setting of bilateral trade that we have seen in the introduction, where we just have one seller with one item and one buyer. And in previous work, in this mechanism template where we fixed this price P, the price P was mainly said to be the median of the seller's distribution. And then you trade the item if the seller and the buyer both agree a trade, hence the seller's value is less than P, the buyer's value is at least P. And by this, one can show that this recovers half of their expected optimal social welfare, meaning that this is a 1/2 approximation. And also by this approach, you can do better than this 1/2 approximation. So in particular, if you replace this 1/2 quantile by just a randomized quantile, you can even recover a 1 minus 1 over E fraction of the optimal social welfare using this approach. In contrast, our approach is different. So what we do is we want to apply profit inequality techniques to two-sided markets. And in particular, we focus on a work which was by Duttinger and others from a Fox paper in 2017, which is called balanced pricing. So how does this work in the setting of bilateral trades? So we fix a price P, which is half of the expected optimum of seller's value and buyer's value. And then we first ask the seller, do you want to keep the item or do you want to sell it? And if the seller says, okay, we'll keep the item, then the mechanism is over and the item remains with the seller. And only if the seller agrees a trade, so the seller says, okay, I will try to sell the item, then we ask the buyer, do you want to buy the item or not? And also in this case, so for those of you who are familiar with profit inequalities, it might not be surprising that this recovers also half of the expected optimal social welfare. So that's just like a direct implication of a profit inequality, which we run on the seller and the buyer as a set of two agents. Nonetheless, I will just give you a quick proof idea why this holds true, which is mainly inspired by the profit inequality proof that is already known before. So let's first see, when does our mechanism extract which value? So the first case is that the seller initially keeps the item so that BS is at least P. Then we can extract the value of the seller. The second case is that the seller says, okay, I will try to sell the item so her value is less than P, and the buyer has a value of at least P. Then a trade occurs and we can extract the value of the buyer as social welfare. And in the last case, where the seller says, we'll try to sell the item, and the buyer says, okay, I will not buy the item because my value is less than P, the item remains with the seller, and hence we can extract the value of the seller as a contribution to social welfare. And what we're focusing on in the analysis is to do not consider any contribution of this third case, but only of the first two cases. So let's define by Q the probability that any of these two cases is happening, so that either the seller or the buyer has a value at least P. And hence with the 1 minus Q is just the probability that the counter event is happening. And then we know that the social welfare of our mechanism, it can be lower bounded by a contribution of P times Q, which is just the probability that one of the values exceeds P, and then we get a contribution of at least P, plus something that is called the surplus. And that is a random variable indicating what the agent who gets the item has for a value exceeding P. So that is like just the value that is not covered below P, but just everything of the value above P of the agent who's allocated the item. So let's bound this for seller and buyer. So what is the surplus of the seller? The seller has a value exceeding P, and hence keeps the item if this Vs minus P term is non-negative. And by this to the plus, I just mean the expression in brackets if it's positive and it's 0 otherwise. And hence, the expected surplus of the seller is just the expression Vs minus P if it's non-negative. And we can get a feasible lower bound by just multiplying this with 1 minus Q in order to get a lower bound on this. And for the buyer, we can do similar things, but a bit more tricky, because a buyer has only surplus if her value VB minus P is non-negative, but also only if the seller did initially agree a trade. So if Vs is less than P. So therefore, we get this additional indicator function in here. But still, we can use independence of those two random variables and then lower bound the probability that the seller has a value less than P with 1 minus Q. So if we plug this in our formula above, what we get is just this expression here, that the social welfare for algorithm is P times Q plus the sum of the bounds for the surplus of any agent. Now we can use that the sum can be lower bounded by its maximum. And now we just plug in our definition of the price. So the price was said to be half of the expected optimum. And hence, we result in a social welfare, which is a half times the expected optimum times Q plus a half times the expected optimum times 1 minus Q, which nicely combines to a half times the expected optimum, showing that this is a 1/2 approximation. Okay, that is very simple for the bilateral trade case, but becomes much harder once we consider more general settings with many sellers, many buyers, and multiple items. And I will show you one example from our paper of match rate double auctions. So in match rate double auctions, we have multiple sellers with identical items and multiple buyers. And again, we have the same setting as before. So any agent has a privately known value for holding one of the items, which is drawn from a publicly known distribution. And then as a mechanism, what needs to be specified is somehow you need to specify traits for prices. So for example, a feasible outcome could be that the first seller and the first buyer trade for some price, and hence the outcome of the mechanism is that there is a bilateral trade between the first seller and the first buyer. In general, in the setting, there are M sellers with M identical items and N unit demand buyers. And as said, over the set of buyers, there's a match rate feasibility constraint, meaning that the set of buyers who's allocated an item in our mechanism needs to be independent in this match rate. And still, of course, what we want to do is we want to maximize social welfare, which is in this case just the sum over the values of all agents who are allocated an item after running the mechanism. And we do this by specifying bilateral trades and suitable prices in order to find a good approximation for social welfare. And I will quickly show you a pseudocode on how this is done. So the set of buyers is denoted by B, and the set of sellers is denoted by S. And what we do is we first, as long as there are buyers and sellers remaining, we first remove all the buyers that are infeasible with respect to the match rate constraint. And then we choose a suitable seller and a suitable buyer and compute a price P for a trade. And this is like kind of the tricky part, and I will tell you a little bit more of this in a minute. But afterwards, what we do is just exactly the same things we did for bilateral trade for this pair of seller and buyer. Namely, we first ask the seller, do you want to keep the item or do you want to sell it? And if the seller says, okay, we'll keep the item, then she keeps the item forever and is removed from the set of available sellers. In contrast, if the seller says, okay, we'll try to sell the item if my value is less than P, then I ask the buyer. And if the buyer says, okay, I have a value at least P, so I agree a trade, then a trade is occurring from S to B for price P, and the item is transferred from seller to buyer, and both agents are removed from the set of available agents. On the other hand, if the buyer disagrees, then only the buyer is removed, and we will never offer a trade again. But for the seller, we can consider the seller in the next round. Okay, so that's the mechanism. And the question is, how do we set those prices and which of the agents to choose? And the pricing in our case is just done by a threshold-based thing. Namely, first, we compute a threshold for every agent, which is PS for any seller and PB for any buyer. And for the seller, this is just the expected value for the seller holding an item. And for the buyer, the threshold is, and that is where this correspondence to profit inequalities and balanced prices comes in. This is the optimum that we can take over all buyers in the match rate, given the current allocation of items. And then we subtract the optimum over all buyers in the match rate, given the current allocation, if we allocate one item to the buyer for sure. And then the price just combines as the sum of these two thresholds, and then we take a 1/3 fraction of it. And you can see that in contrast to what we've seen in this bilateral trade case at the beginning, that now prices are changing dynamically over time. And hence, things become much more complicated to get a dominant strategy incentive compatible and strongly budget balanced mechanism here. And that is exactly where our choice of seller and buyer comes in. So we choose the seller who has the currently lowest threshold PS and a buyer who has the currently highest threshold PB. And then we offer to those two agents a trade. And now note that this is dominant strategy incentive compatible for any buyer, because for any buyer, we just offer a trade at most once. And hence the buyer can accept or reject, but it's always utility maximizing to report the true value. And for the seller, the argument is that we can offer trades multiple times, but the price for a seller is only decreasing over time in the ongoing mechanism. And hence, as a seller, you will try to sell your item as early as possible if you want to do so. And eventually, at some point in time, you will just say, okay, I will not sell the item anymore because now my value is at least the price that you're currently offering. And hence, as a consequence, we get by this choice of buyer and seller that we can construct a mechanism which is dominant strategy incentive compatible and strongly budget balanced. And in addition, that is a 1/3 approximation with respect to social welfare. Okay, let's conclude. What have we seen in this talk? We have seen that profit inequality techniques are very useful beyond the one-sided environment. In particular, understanding the one-sided environment case first, properly, and then afterwards trying to extend these techniques to more general settings, so in our case, the two-sided markets, is a very, very nice way to tackle problems. And as we've seen, by this, we could improve the state-of-the-art approximation guarantees in several settings. So for matrix double auctions, combinatorial double auctions, and knapsack double auctions. But still, of course, we were not able to solve all the problems, but there are a lot of problems open that we could not answer in our paper. So for example, for matrix double auctions, the mechanism that I just have showed you needs to pick agents in every step, like in a suitable chosen way. So it cannot be implemented online because we have to pick a buyer from the set of remaining buyers in every step. So the question is, in our paper, we have another mechanism which is only weakly budget balanced, gives a 1/2 approximation, but is implementable online. So the question is, can we combine the best of both worlds and get an online mechanism for buyers, which is strongly budget balanced and a 1/2 approximation? Or as another question for future research, we have seen that using that quantile approach, you can get a 1-1/E approximation by using a randomized quantile instead of a deterministic one. So could also we, by the approach of profit inequality techniques, can we also improve the approximation guarantees for, let's say, bilateral trade, or for matrix double auctions, or knapsack double auctions, or whatever, by using randomization instead of our deterministic prices? Okay, I hope you have fun reading our paper. Thank you very much, and stay safe.